So the question asks about find a formula for the inverse function y equals e to the 1 minus x. So using the strategy I like to use, I switch x and y. So now I have x equals e to the 1 minus y. And okay, the problem now is how to solve for y. So for problems like this, we have a log, we have an exponential function. You typically want to use the log function. So I'm going to take the natural log of both sides. Okay. Now, over here, I can move this exponent in front. It's just one of the log rules. So I get 1 minus y times natural log of e. And I think I even mentioned this. It's good to know that the log to the base b of b is 1. Well, here we have natural log is the log to the base e of e, so this is 1. So we just end up with 1 minus y. So from here, I've got log x equals 1 minus y, and I have to solve for y. Is that enough? Should I finish it?
Yes. No. I messed up. I actually didn't take the natural log of both sides, you know what I mean? That's just a huge mistake.
That's okay. All right. Any other questions on the homework? Okay. There will be an assignment, new assignment posted today, sometime later today, worst case tonight, and that'll be hopefully for next Tuesday if you can. So the main topic for today is something called continuity. Let's call it right, continuity, yeah. Before I launch off into continuity, I'm going to digress for a second on a bit of notation. Interval notation. I'm actually going to throw a bunch of notation, any of which you might know or might not know. In math, we often use curly brackets to mean a set. And we might write a set in various ways. We might put in values, right, 1, 2, 3, 4, 5. Clearly, that's not going to work with an infinite set. We can't list them all. But we might say, so x, and I'm going to use this symbol here, which means a member of. And then I'm going to say, I'm going to use R with a little fancy font here, which is what we use to mean all real numbers. And that might suffice if I meant all real numbers. This is the set of all real numbers. I might simplify this. I might just write this. That's all real numbers. But I might want to be a little more specific. So I might put a colon here, which means such that. And then I might specify here. So I might say x is less than 0, greater than 0, less than 1. And now I have this definition of an interval, the open interval from 0 to 1. But since we're going to use this, we're going to use intervals quite a bit. We're going to talk about them. When we talk about a domain or a range, we might use intervals. So we have a shortcut, which is we can just say parentheses 0, 1. Now, this does not look any different from the coordinate 0, 1, x, y. So to know which I'm talking about, you need a context. Right? So if I say, you know, the domain is 0, 1, you know it's an interval. Similarly, and you see, we have all these different ways of writing this. Some are a little more brief, some are a little more specific. This is very specific. But I could just write like this. You would just assume I'm talking about real numbers because this is a calculus class and we really don't deal with complex numbers or other kinds of numbers here. And the shortcut for this is instead of using parentheses, we use square brackets. So this is now what we call the closed interval, 0 to 1. And since we're going to use that term a lot, I want anybody who's unclear on what an open interval and a closed interval is. If you're drawing a number line, you might draw an open interval by putting little circles like 0 and here's 1. If you're talking about a closed interval, you might put a little solid dot, or some books will, they'll just put like parenthesis here to mean open and brackets to mean closed. All these are possible, just as long as you understand the basic idea. An interval is just all the numbers between two endpoints. And we might include the endpoint in a closed interval, or we might not be including the interval, the endpoints in the interval. Just in case anyone hasn't run into it, there's one more detail here. If I were to say x is greater than 0, so that means all real numbers greater than 0. So 0, well, what do I put here? Well, infinity. And for reasons, we always think of an endpoint of infinity being an open interval. There's no endpoint, infinity endpoint. Similarly, doing an open interval here, well, this could be infinity. There's nothing wrong with having a hybrid here, one end open, one end closed. And, just since I've already given you two versions of all real numbers, you could write this as from negative infinity to infinity. It's also valid. So everything you ever wanted to know about intervals. Any questions about this? Because it's just notation. It's just a way of indicating a certain group of numbers. And we're going to run into it today. All right. Okay, so continuity. This is just one more hurdle we need to get over before we get to the good stuff, the fun part of this class, which is differentiation. This word continuity, in everyday language, it means something that goes on without interruption. And we have a similar meeting in mathematics. In a very rough way, you have a function and you can graph it with a pen or pencil or marker without removing the marker from the board, then it's continuous. That's very intuitive, very rough, not very accurate from a mathematical point of view. But, you know, as a kind of a first level way of thinking about it, it should work. We're going to talk about 3 different types of continuity today. First is one we're going to actually have to think about a little. Is continuity at a point, which we'll also call pointwise continuity. And that's the first thing we're going to go over in a minute. Second is continuity on an interval. So you might have a function, and might not be continuous everywhere, but on a certain interval it might be continuous. So we have continuity on an interval. And finally, we could have continuity of a function, f of x. And what we mean by that is the function is continuous everywhere on its domain. So it doesn't have to be continuous on all real numbers if the function isn't defined there, but wherever it's defined, it's continuous. All right. So now we're ready for our basic definition, which you'll see is intimately involved with limits. We say a function is continuous at a point C if, and this is a definition, I guess I should specify, if the limit as x approaches C of f of x equals f of C, the value of the function at C. See that? So, nice copacetic. We've been looking at a lot of functions or a lot of limits, where the limit ends up being exactly the value of the function at that point. Not always. And here we now have the definition for function being continuous at a point is exactly that. If the limit as you approach that point is the value of the function at that point, then it is continuous at that point. There's no requirement that this be the case for some function. For example, let's consider the limit as x approaches 1 of x minus 1 over x minus 1. Well, this limit is clearly 1. But this function is not defined at 1. 1 is not in its domain. So the function is not continuous here. Now, I could redefine this function this way. I could say f of x equals x minus 1 over x minus 1, where x is not equal to 1, and f of x equals 1, where x equals to 1. This is a perfectly good function, and it's continuous, not just at 1, it's actually continuous. It's a continuous function. It's continuous at every point. The only point that's even interesting is at 1, and we fixed it. Okay. Jump right in. You know, this is new to you. It's a little, I'm sure it's a little abstract, a little odd. Just jump right in if you have any questions about it. You can see it for a minute. All right, so as we're going to see in a few minutes, most of the functions you're used to dealing with are continuous, if not everywhere, almost everywhere. But we want to talk about, just want to reiterate this definition again. Definition of continuity at a point. To fulfill this, we need three things. We need one, function is defined at C. Number two, limit exists. We'll call it L. And three, L equals f of C. Okay. You fail any of these, and your function is not continuous at that point. Okay, so what can that look like? We could have a function that kind of looks like this. You have some point C here where we're coming along, and all of a sudden it jumps to some other value. This is an example of a discontinuous function. And in particular, we call this it's called a jump discontinuity. A good example would be, if you know, there's a function, it's written like this, means the greatest integer less than x. And this is what we call a step function. I guess it would be this. And it has many jump discontinuities in it. This is a useful function when you're thinking about the way you probably, everybody here probably has unlimited calling, but we used to have, used to pay for phone calls by the minute, and they charge you as soon as you start talking, and then as soon as you got to the end of the minute, it would jump up. It's an example of this function. Okay. Another function I think we looked at briefly, called the Dirichlet function, named after a famous mathematician. Well, again, I can't draw it very well. Draw it like this. It's the function where f of x equals 1 for x rational and 0 for x irrational. And I think we talked about this with respect to limits. Any point on this, the limit as you approach that point, the limit doesn't exist because the function just keeps jumping up and down. It doesn't get close to any point. So not having any limits is really discontinuous. It's discontinuous at every point, and so we would say discontinuous everywhere. Function that's discontinuous everywhere. So that's the second example of a discontinuity in a function. In this case, a completely discontinuous function. The third example is the one I erased, even though I didn't want to. You have a function where either function is just not defined at a point, or it might be defined, but that point might be somewhere else. And here we have limit as x approaches c of f of x is not equal to f of c. I mean, this might be 2, and we're exactly defined as 3. So it's just has a single point, and we can fix this. We can make it continuous by moving this point or defining this point. And this is called a removable discontinuity. It's removable in that you can redefine it, the function, and it becomes a continuous function at that point. All right, so what do we have? We have jump discontinuity, discontinuous everywhere, removable. We have one more type of discontinuity to consider. Let's take a look at the function f of x equals absolute value of x. No. Over the absolute value of x. So, as we get close to x from this direction, this gets close to, this goes up to infinity. We get close to x from this direction, it also goes up to infinity. The function is not defined at 0. So it's continuous everywhere else, but it's not continuous here. And it's not repairable. It's not a jump discontinuity. We call this a discontinuity at infinity. So you're going to have to be able to recognize these kinds of discontinuities. There'll probably be some homework problems on them. We're going to look at some examples here. Questions you asked. way, Dirichlet function is kind of fun because it, it kind of throws a wrench in the works math all over the place. There are other functions like this, really bizarre, but you won't get any homework or exam problems using this. This is mostly just so you get a feel for this. Okay. Example. F of x equals x squared minus x minus 2, x minus 2. So the question is, where is this function discontinuous, and what kind of discontinuity does it have? Well, we know already there's likely to be a problem at 2, right? This is a polynomial function. Its limit is defined everywhere but at 2. I'm sorry, a rational function, a polynomial over a polynomial. But in this case, if you see a problem like this, you want to be a little skeptical here. Let's try plugging 2 in here. So 4 minus 2 minus 2 is 0. Oh, 0. Well, that means 2 is a root of this polynomial. So we should be able to factor it. So let's do that. This will succumb to a very simple reverse FOIL. It looks like 2 and 1. Now we just have to figure out, we know there's going to be a plus and a minus because there's a minus here. We just have to look and say, all right, where does the plus go, where does the minus? Well, if I do it like this, right, the FOIL tells me minus 2 plus 1 is minus 1. So this is my function. And we can see here that the limit as this function goes to 2, well, this is going to cancel out. And so the limit is going to go to 3. But the function isn't defined there. So it's, what kind of discontinuity do we have here? Anyone thought on that? I mean, it's not at infinity and it's not everywhere, so what's left? It's either a jump or it's a removable. Yes? It's removable, yeah. Let's look at the function that removes it. So for x not equal to 2, what do we want this to be? We want it to be equal to 3. Okay. This function looks like x plus 1, except that 2 has got a hole in it, and we just fill it in. We just say it's 3, that x equals 2, and now we have a continuous function. Yes?
Why 3? Where did you get the 3 from? How did you do this?
Yeah. So limit as x approaches 2 of x minus 2 over x minus 2 times x plus 1. This is the limit now, right? I know it's not defined at 2. The limit here is going to be 1. X over 2 minus x over 2 goes to 1. And x plus 1 is going to go to 3. So the limit is 3. Okay, that's fine. Well, okay, if you want to do bad math, say, here's my function, x minus 2 over x minus 2 cancels. You see why it's bad? I mean, I'm canceling 0 over 0, but that's the way to figure it out. Right? Just as long as you're aware. This function is not defined at 2. This one, oh. See? I'm dyslexic on the answer. So at 2, I define it as 3, and it kind of completes the function at that point. Since its limit is 3 at that point, it's continuous at that point. And everywhere else, it's a rational function that is continuous everywhere. So all we did is we just kind of filled in that point here, which happens to be a 3. Let's look at another example. Question is, where is this function discontinuous? Function is 1 over x squared, x not equal to 0, and 1 if x equals 0. Okay, so question is, where is it discontinuous? That should be obvious. And what kind of discontinuity is it? This, wait a minute, 1 over x squared. This, then at 0 is just going to point over there. Anyone? Yes? Yeah. It's way up there that it doesn't connect, right? Out in outer space. All right. Okay. So we've been talking mostly about discontinuities at a point, or continuity at a point. We need a few definitions here to round this out. Continuity on an interval so the definition is function is continuous on an interval if every c in that interval function is pointwise continuous. At C. Okay, that doesn't really add anything technical or difficult. So we know what a continuity at a point is. The limit as we get to that point is equal to the function at that point. and it's continuous on an interval if every point on that interval is continuous by the first function, by the first definition. And then finally, definition of a continuous function. Continuous function. Function. I guess I'm just going to leave this here. That is continuous. That is pointwise continuous. At every point in the domain of the function. Now, there's a, before we look at some examples of continuous functions, functions on intervals, I want to just say I am cheating a little bit here. Say I have some function and I define it on some interval. And I say it's a continuous function. Some f of x. Well, you might come to me and you might say, wait a minute, Mr. Schoenbrun, what about these endpoints? The endpoints are one-sided. They don't have a left and a right limit. So they don't really have a limit, so by your definition, they're not continuous at that point. Well, okay, I'm going to hand wave a little here. There is such a thing as a left-handed limit. We talked about that, and a right-handed limit. And there is an analogous idea of left-handed continuity and right-handed continuity. And I'm just not going to be very picky about this. If I have a function that's defined on an interval, we can say that, and it's otherwise continuous. We can say it's continuous. We don't have to fret about endpoints. We can wait for a higher level math class and be picky about that. Okay, so it turns out that in our math background, most of the functions we've dealt with are continuous functions. That's going to turn out to be really nice, because when we want to find the limits at those functions, if we know they're continuous, we just evaluate them at that point. We don't have to worry about some tricky formula, or as an example, we have to factor one of the polynomials. So okay, so all polynomial functions are continuous functions. Let's say continuous. Absolute value functions. So if we have something like x equals absolute x, let's look at this. Well, straight lines are polynomials, so there's no problem with those. This is the only interesting point. And if you think about it, the left-hand limit and the right-hand limit, say meet, it's a continuous function. Root functions. F of x equals n of x, where n is some integer greater than 1. Exponential functions. F of x equals e to the x, f of x equals 10 to the x. These all kind of look the same unless you put a negative sign there. They're all continuous. They're inverse functions, log functions, natural log of x, log the base 10 of x. Now, you might go, wait a minute. That was down here at 0. This function is not continuous at 0, but 0 is not part of its domain. All right, remember, function is point continuous on every point in its domain.
That last one was a log function? That last one that you just raised, like that one, it was on the bottom, it was in like the third and fourth quadrant. It was like,
Yeah, I apologize, I'm just between my hearing and the mask. Let me see if I can turn this up, if that helps. Say again?
that last one that you just erased,
Yeah,
that was a log function, right?
that was a log function.
Okay.
Yeah, I'm just going to put it back for, I did state it's an inverse function, right? So remember that inverse functions and their function are reflections across y equals x. It's always a good feature of inverse functions to know. Okay, 6, rational functions. P of x over q of x, where q of x is not equal to 0. You can spend a lot of time drawing rational functions. Sometimes they'll have horizontal asymptotes, vertical asymptotes. You might say, well, what about where q of x is 0? Well, where q of x is 0, again, it's not part of the domain of the function. So all rational functions are continuous on their domain. They may have points of discontinuity that aren't in their domain. And our friends trig functions. So we have a sine function, cosine function, tangent function. What does a tangent function look like? Again, it has these places where it goes to infinity or negative infinity, but they're not in the domain of the function. So everywhere but those points, these functions are continuous. Here the tangent function, I guess, goes to infinity at pi over 2, and here pi over 2. And I don't know, I guess I haven't really stepped on these yet, so I might as well. I want to graph the cosecant function. That's 1 over the sine of x. So a good way to graph this function is to first graph the sine function. It's not very good drawing. And I draw a line here at 1 and -1. And then our cosecant function is going to meet at 1, and it's going to go up. And down here, it's going to meet at -1 and go down. Just in case you're familiar with these. Secant function is 1 over the cosine, same idea, only cosine. And again, continuous everywhere on the function except, on its domain, except this point is not in its domain, or we're not using it in our definition. And lastly, inverse. Trig functions. Now, this might be a moment to just review this idea. I have the sine function. Clearly, if I invert this, I find a reflection over x equals y. It's not going to be a function. Like this. So we make it a function by restricting the domain on the sine function. And we just have we have a function on a particular interval that we would call the inverse sine function. And if you use your calculator and you say inverse sine of something, it's going to use, we have a very standard way of limiting the domain. You should be aware of this. The domain of the inverse sine is going to be what? Well, the domain of the inverse sine is, -1 to 1. But its range is going to be negative pi over 2, pi over 2. Actually, it's a closed interval. And likewise for the cosine, we have a different interval tangent. Oh, the tangent function is kind of nice. When you invert the tangent function, you get something like this. It's defined on all reals. And it goes to pi over 2 and pi over 2. All right, so I'm going to stop here and take a break.
I want to give all this.
And then if you have
Yeah.
Okay, so this would be a pretty light kind of question based on what we've been looking at. We have some function, 1 minus square root of 1 minus x squared. We want to show it's continuous on this interval here. Okay, so how would we go about that? Well, first thing to note that if c is in this interval, then f of c exists. It's defined. So that's good. So what we want to do is we want to see if the limit as x approaches some c in this interval of 1 minus the square root of 1 minus x squared, we want to see if it exists. Well, that's easy enough. It's defined everywhere, so it's going to exist everywhere. But we also want to know that it's equal to the function at c, which is 1 minus square root of 1 minus c squared. So there's a little hand waving here. Seems like, but we're going to use our properties of limits, right? You know that the limit as x approaches c of 1 minus square root of 1 minus x squared is equal to the limit as x approaches c of 1 minus the limit as x approaches c square root of 1 minus x squared. How do we know that? There was that limit law. You know, if you want to think of it as plus the negative of this, that's fine. Or you can divide a limit up, you know, if it's a plus or a minus. 1. Well, we know what the limit as x approaches c of 1 is. 1's a constant, so that's just 1. So that's no big deal. Okay, we did have a limit law about roots, right? The limit as x approaches c of the root of something is the root of the limit as, in this case, 1 minus x squared, x minus c. And again, we can divide this up. The square root of the limit as x approaches c of 1 minus the limit as x approaches c of x squared. And again, the limit of 1, constant, is just 1. And x squared is a polynomial. And polynomials are continuous. So we know that this is just going to be 1 plus square root of 1 minus c squared. That's kind of long and drawn out. You could have just looked at the original function and said, yeah, everything here is going to glow, we can just plug it in. So it's going to be continuous. So that's how you would, you know, if you were given that kind of question, show me that this is continuous, either the function is continuous or continuous on an interval. Right. Example here. We have a function f of x is continuous. And I want to show that, and k is a constant. Show that k times f of x is continuous. we show this? Well, we know for C member of the domain of F that limit as x approaches C of f of x is f of C. So we can certainly multiply both sides of this by k. But then we have a limit law that says k times the limit of this function is just the limit times k. And this shows you that k f of x is continuous. Okay, so let's write this down over here. This is the first of some laws of continuity that are equivalent to limit laws, which is, f of x is continuous, k times f of x is continuous. Okay, so now, there are a number of these, we'll call them rules, that transfer right over from limits. Assuming f and g are continuous functions, we have f plus g, which is continuous. Continuous function. F minus g is continuous. Again, you can show these the same way we did the example over there. You use the associated limit law, and you show that you get an expression like, well, that the limit is x approaches c of f of x plus the limit is x approaches c of g of x. You just have to show that that's the limit is x approaches c of f plus g of x. It's just the limit law, and you get continuity. Similarly, f times g is continuous. This rational function f over g is continuous, where g of x is not equal to 0. You could say on its domain, since for g is 0, it's not part of the domain of this function. Lastly, if f and g are continuous functions, then f of g of x is continuous. That would have helped with our example, I think. The example is 1 minus square root of 1 minus x squared. Well, if we write this as a composition of functions, f of x equals 1 minus x. G of x is squared, 1 minus squared, and then maybe say x of h of x is equal to 1 minus x squared. Well, these are all three continuous functions, and so we could say f of g of h of x is continuous by a composition. All right. Take a look at some actually pretty simple problems here. Now that we have all this hardware, this equipment that we can use and bring to bear, let's find the limit as x approaches -2 of x cubed plus 2x squared minus 1 over 5 minus 3x. So now this problem is actually quite simple. If we look at this rational function, we see that we plug in -2, we get 5 minus 6 or 11. So -2 is in the domain. And since this is a continuous function, we know its limit is the same as the function at that point. So we can just write this as -2 cubed plus 2 -2 squared minus 1 over 5 minus 3 times -2. Okay, so what do we got? -8 plus 8 minus 1 over, say, 11. So it's just minus 1 over 11. Is the math right? Yeah. Right. Question about what I just did? It does seem it does seem like I'm just telling you something you knew already, right? But we're now kind of we're putting it in this language of continuity. Let's try one more. Yes.
What did you say about the domain a minute ago? Says something.
Okay, so this is a rational function, and its domain is x is a real number, where x is not equal to what? Well, where 5 minus 3x is equal to 0. This is our p of x. So where is that the case? That's x equals -5/3. So not equal to -5/3. So -2 is not -5/3. So it's in the domain here. And if it's in the domain of a continuous function, you can find the limit at that value, at that c, by just evaluating the function at that c. It's one of those things where you look at that and go, wait a minute, that's too easy, that's too obvious, right? It does seem that way. But we're down in the trenches here trying to get this vocabulary together so that when we run into something that's more interesting or difficult, we can parse it apart and see where the problems are. All right. Except for maybe using some scarier functions, I hope not. Let's find the limit as x approaches pi, sine of x over 2 plus cosine of x. So again, we're using the fact that if f and g are continuous, f over g is continuous where g is not 0. Well, 2 plus cosine of pi I want this to be a tricky question. Somebody tell me the cosine of pi. Have it off the top of the head. Don't tell me. Just be honest. If you know off the top of your head, just raise your hand and smile under your mask. Just a few. So, you're doing calculus and there's a problem with sines and cosines, and you need a way to deal with this. Well, let me go back to the unit circle. And remember that any point on the circle, theta, cosine theta, sine theta. Those are its coordinates. So you think, all right, pi, what's that in radians? In degrees. Well, we multiply pi times 180 over pi, and we get 180 degrees. Okay. I think people can put their hands on 180 degrees, right? Up to here is 90 degrees, all the way over here, that's 180 degrees, or that's an angle of pi. So it's this point over here we're worried about. What are its coordinates? They're -1, 0. Well, okay, -1 is the cosine. So cosine of pi is -1. If you need help with that, come to office hours or come to the there's been some juggling around with when and where the math help is down in the math office or wherever it's going to be. If you ask Christine down in the math office, and I know it's still going to be Tuesday and Thursday afternoons. There may be some other times now. But if you need help with this stuff, don't wait for the exam. You can come to my office hours, you can go over it. Or you can just go back and look it up on the web or look up a pre-calculus class. Just make sure if I say like, I don't know, 3 pi over 4. What's the sine and cosine of that? 3 pi over 4. That's down here. That's 0 kind of -1. So the sine is -1 and the cosine is 0. You should be able to put those together. All right, so cosine is -1. The denominator is 2 plus -1 is 1. So it's never 0. So sine is continuous everywhere. Cosine is continuous everywhere, and this fraction is continuous everywhere. This is a continuous function, continuous on all real numbers. So all I have to do to find the limit is evaluate it at the function. So I just need to know sine of pi over 2 plus cosine of pi. Well, that's easy because sine of pi is 0. So this is just 0. Yes?
3 pi over 4 is in, I think, the second quadrant. What you marked is 3 pi over 2.
Just let me know what flavor truffle you like. Yes, thank you for correcting that. That's exactly right. Somebody's paying attention. Okay. All right, now, having had all this continuity thrown at you, we have a few new things we can do with it. We're going to go over two important theorems in mathematics, calculus, analysis. And again, they're going to seem obvious, but they're now well defined. We're going to define them exactly, and we're going to be able to use them. So the first is called the intermediate value theorem. And it says, if f of x is continuous on some interval a, b, and capital C is a number where C is less than f of a and greater than f of a, less than f of b, then there exists a small c, and I should say at least one, where c is between a and b, such that f of c equals capital C. I think the picture here is, it's not worth 1,000 words, but it's a lot easier to see what's going on. So I have some function, I have a point A on it, I have a function at A, I have a point B, a function at B, and I have some value here C that's between a function of A and function of B, and the intermediate value theorem says if this function is continuous, then there must be some C down here such that f of C equals C. Another way of saying it is all the points are, we pass through all the points between A and B as we go from f of A to f of C. F of A to f of B. The important restriction here is this has to be a continuous function, right? This were, that step function I mentioned. We could have plenty of like C's here where there's no C where the function reaches that value. But of course, this is not a continuous function, so that's not a surprise. Okay. So we can do some nice things with this. Very simple things, but nice. Problem. Show that 4x cubed minus 6 squared is 3x plus 2 equals 0. We're not going to solve this. by the way. What we're going to just show is that there's a solution on the interval from 1 to 2. That's what we want to show here. How do we show that there's a solution between 1 and 2? Well, let's look at this as a function. And now let's look at f of 1. That's 4 minus 6 plus 3 plus 2. 9 minus 6 is 3. And f of 2 is 4 times 8 minus 6 times 4 plus 3 times 2 plus 2. What's that? 32 minus 24. Oh goodness, I'm going to get the simple math wrong. Oh! Function wrong. Math. What's this again? 7 minus 8. 6. Yeah, except my notes are wrong. Minus 1. Okay, good. And 13 minus 24 plus 6 plus 2, 8, 10, 16. Okay, so what do we got here? We got A is 1. No. Sorry. Yeah, A is 1. And B is 2. And f of A is, well, that's negative 1, right? Negative 1. And f of B is 16. And we want to know that there's a solution to this, which is f of x equals 0. So my big C is 0. I'm sorry, my C is 0. The intermediate value theorem tells me there has to be a C on here, where C is 0, because we have to pass through all these points. Yes?
Is there a two value in this? The n is supposed to be -2, but then
Right. Thank you. All right. So, we haven't found the solution, but we know there is, because it's continuous. So that's what the intermediate value theorem gives us. Right? I think I'll leave that theorem up because we have another one that's useful and important. And a little obvious, I think. Okay. This is called the maximum minimum theorem. So if f of x is continuous on the closed interval a, b, we're going to see in a minute why it has to be a closed interval. Then f takes, f of x takes a maximum value capital M, M, on the open interval AB, and it takes a minimum value, little m, on A, comma B. Now this seems kind of obvious. If I have some function, has two endpoints, it's continuous. Somewhere along here is some maximum value and some minimum value. It might not be at the endpoints. Function might go like this. We have a max here and a min here. Does it have to be continuous? Well, it might have a maximum and minimum if it's not continuous, but what happens if it kind of goes like this? It has a discontinuity at infinity. Well, then it doesn't have a maximum. But it's not continuous, so that's part of this. Now, what happens if we don't have a closed interval? And we just have some interval AB. What can happen? What can go wrong? So, consider the function tan of x on the interval minus pi over 2, pi over 2. So it's a continuous function. It's continuous on its domain, which includes this interval. What happens to this function? Well, as we get close to pi over 2, it kind of shoots off. And as we get close to negative pi over 2, it also shoots down. So you need this to be a closed interval. If you have a closed interval in a continuous function, you know it has to have some maximum and some minimum. That's the section on continuity. We're going to be using it shortly. We have a little fill-in topic. We'll kind of complete our knowledge of limits for the time being. Are there any questions on this before I move on? Yes.
I'm not sure if the one up there is right, but can you draw another graph for the maximum and minimum theorem? Like what it collapsed on the graph?
Well, you draw all kinds of graphs. I think you have, remember, it's between two endpoints. You know, whatever you like. As long as it's continuous, it has to have a max and it has to have a min. All right, anything else? All right. Honestly, I don't know why Stuart does this in this order, but I'm kind of constrained to follow the order Stewart does things where all sorts of problems crop up with problem sets, so that's why we're going back to limits for a minute. This is section 2.6, which is limits at infinity. This is not to be confused with yet, with infinite limits. You'll recall that if I have, say, the limit as x approaches 0 of, over x, right? You have a limit, well, say from the right-hand side. This is going to be infinity, right? It's just going to keep getting larger and larger. That's not what we're talking about here. So instead, let's look at the function f of x equals x squared minus 1 over x squared plus 1. And let's think about what that must look like. So this is always positive, so it's defined on all real numbers. And at 0, this is minus 1. Back to 1, it reaches 0. And also at minus 1, it reaches 0. And now we know it's continuous, right? Because it's a rational function. It's continuous on its domain, which is all real numbers. So it'll be kind of a straight line. What happens when this x gets very large? Well, you can see that as x gets very large, we can put in a big number, say 100. So now it's 10,000 minus 1 over 10,000 plus 1. So now here at 10, it's very close to 1. That's kind of the nature of the function. The larger x is, the closer this gets to 1. Similarly, if we go in the other direction, it's also getting close to 1. So we have this notion of a limit at infinity. We would write it this way. Limit as x approaches infinity, f of x equals 1. So again, the idea is we're getting closer, the larger x gets, the closer we can get to some value. Using this idea of epsilon deltas, if I pick an epsilon, like I want to be within 0.0011. In this case, it's not finding a delta, it's just finding an x. And I find an x that pushes me out to where I'm not just closer than that number, but I'll always be closer. And that's this idea of a limit at infinity. We just look at this inverse tangent of x. Kind of looks like this. So if I want to look at the limit inverse tangent, the inverse tangent as x goes to infinity, you can see that this is, it goes to pi over 2. If I want to look in the other direction, x goes to negative infinity. This is going to go to minus pi over 2. Again, given some small difference from pi over 2, I can find an x where the tangent of x is within that small epsilon. I kind of hinted at this. There is a formal definition of a limit at infinity, just like we have this delta epsilon definition. But you're not responsible for the delta epsilon definition. I'm not even going to give you the definition here. We're not going to use it. But we're going to go on in mathematics to do a formal proof using that definition. All right, so what can we do with this idea? Well, erase this. This is not what we're talking about. So we can look at something like this. Limit as x approaches infinity of 1 over x. What does that look like? 1 over x looks like this. So is this obvious what this limit is here?
0.
0. Sure. Because we never reach 0. Further we go, closer we get. We can always pick an x that gets us as close as we want from then on. Similarly, x approaches infinity of 1 over, oh, but I don't have to stop here. All right, no homework on infinite limits. We'll finish up on Thursday.